Hi, my name is Brian Bittner, and I'm presenting my CS112 term project called ULabel. So before we look at the program, I'm going to show you what my project's about and how it assists the robotics field. So here's some research being done at Carnegie Mellon. I'm going to let you guys watch this video real quick. Um, this is a vehicle driving through an urban environment. It has a 3D laser and cameras attached to the top of it, and it takes in data um, as it's driving. And the idea is that a robot will take in this information and make decisions based off of the information that's coming into it. But after a test run, it wants to know whether the decisions it made were correct. So they need people to label ground truth data in order to run testing statistics such as accuracy, precision, and recall. So that's where the labelers come in. And the labeling software that people use now, most commonly for 2D images, is called LabelMe. It's free, and MIT has developed it. And what it is people upload their image repositories to online and then label them there. And what they do is you just click around an image, and after you click around it, you can designate it as whatever you want, and that way it'll assign to each pixel value a label, and then the robot's able to take that data and run the testing statistics I was talking about earlier. Now, a disadvantage of this is it takes a long period of time to be able to write the outlines of all of these parts of the pictures. As a matter of fact, I spent an entire fall doing this, and it was not fun at all. It took a really long time to do each image, um, and it would be a lot easier if you were able to make a program that made this process run faster, and that's what my program accomplishes. So we'll show you guys that now. Okay, so let's take a look at the program. So it's titled ULabel, and it's an image labeling tool like we discussed. And it's different from LabelMe, the program I just showed you, in the sense that the user is able to label a pre-segmented image. And that's what these three modules allow it to do. What that means is that the user doesn't have to draw the outline of the portions of the image he wants to label. He can just click on a section, and it'll highlight, and he can designate that section with a label, and it'll write that to file. So there's a lot of pre-processing involved to set that up, and that's what these two modules do. But first we're going to take a look at the labeler to look at how the labeling process is done and what the final product looks like. So there's a few features implemented in the labeler module. On the right side you can see the four pictures are the last four images that I labeled using this labeling module. So I can show you what the labeling process looks like if I load one of the files up. Something to keep in mind is that all the images I'm using are from Microsoft's research database for object detection. So a lot of universities use these pictures specifically to keep research consistent and to be able to share results with other universities. So, okay, here's the image. And so the whole point of the idea of this is so that rather than clicking around this region of the door to segment it and label it, I can simply click on the door, segment it, and then I can label it. I also implemented a zooming feature and a moving feature, so you can look at different parts of the label and of the image and label parts that would normally be harder to label, like the hood of the car or the bumper or something like that. So you can take a look at what labeling the image is actually like and get an idea of how long it would take to label an image of this complexity. So simply all you have to do is click on the image that you want to label, type the designated label into the space, and then assign it. And then you can keep doing this for all portions of the car and its surroundings. So I'm not going to do the entire image, but this is just to give you an idea of how long it would take to segment the entire image. So I can get this bush here and even the brick wall behind it. It's really giving me a detailed segmentation to work with. And so here's the building, I can label that too, and even the individual windows, I can label those too. So once you're finished, you can simply click on Save Annotations and it'll write it to file. So now we're going to take a look at the other two modules, which allow this image to be segmented in this fashion so that the user doesn't have to go through outlining the object. And the reason for the implementation of those modules is so that the user can provide the segmenter of a large repository of files overnight, get them segmented overnight, and then solely do the labeling process while they're working. That would cut down significantly on the amount of time it takes to label each image. Therefore, robotics projects would have a much larger supply of the ground truth that they need to develop better statistical evaluations of their methods and eventually produce a better product. The quantization lab allows for a pure image to be further generalized into a format that's more easily handled by the auto segmenter. How it does that is it takes each pixel and compares it to all other pixels in the image, and it finds a grouping of pixels that lie within a certain threshold. In this case, it's 60, and this value of 60 is held for each RGB value. And if both pixels in a given instance lie between this threshold, then they're categorized in the same grouping. Each grouping is giving a generalized color, and then that color is output into the resulting image. And we can look at that right now. We can run a simulation. I'm going to use a smaller image so that we have enough time to look at it and analyze it. So as you can see in this image, it's fairly detailed. It's just like a normal picture that you would see with a high, very large amount of different pixelation values. And what you'll find is that once it's quantized, these will be generalized into more specific values for a grouping of pixels. The reason for this is so that auto segmenter can more easily find pixelation differential thresholds when it's looking to segment the picture into different regions, and we'll discuss that algorithm once we get to that module. But as for now, we'll just look at how the quantization lab looks. Once it's done loading, I'll show you what the result looks like. Okay, so as you can see in the image, more specifically if you look at the sky, you can see that the pixel values have been changed to a more generalized format. Like the sky is approximately 4 different colors, whereas it was a wide range previously. And the auto segmenter is able to easily handle this because the pixelation differences are more defined and easier to detect with less contrast between each pixel by pixel calculation. Now, the user has the ability to toggle which threshold he wants to use, like I'm doing now. And for example, if you set it to something like 255, 254, what's going to happen is the entire image will appear as just one color because all the pixels will be grouped into the same grouping because there's only 255 possible values. Whereas if you selected 0, the entire image would stay the same because none of the pixels of any delta values would be organized into the same grouping. So let's pick a slightly larger value and see how that changes the image that we're analyzing. So I'll upload the same image and we can look at the difference. And I'll wait for that to load and then we can look at that also. Okay, so you can see here that the image was generalized to a much smaller amount of pixelation values than in the previous one, whereas most of the grass in this region was all categorized as one color. And most of the sky, the same result, whereas you can see the skyline's a slightly lighter color. And that's how the quantization lab works, and you can continue to manipulate this threshold until you get an image that you think is suitable for the auto segmenter.